Hi, everybody. Welcome. It's my distinct pleasure to introduce George Hunt from the University of Washington. George and I go back many decades. I don't want to think about that. He probably doesn't either. We actually met in the Bering Sea in the Aleutians. I was getting off a research cruise, and he was coming on. My investigator asked me if I would meet with George over lunch, and we did. And we've had some really fruitful proposal writing after that, and many enjoyable times in the Bering Sea. George is a local. He's a Mainer. Went to Harvard, and from Harvard he went to University of California at Irvine, where he spent 35 years in their Ecology, Evolution, whatever department. And then he went up to the University of Washington after that. And I always accused George of being a bird guy, because that's what he focuses on a lot. But he's much more than a bird guy. I think he is a systematic ecologist, looking at the whole system, which is much more than a lot of us do. And that's why I think he's really smart and knowledgeable about these kinds of things. And a lot of his work focuses on as you see up here, bottom-up control of food webs, and looking at the whole system. And I hope George is going to talk about all of that today. So without further ado, George.
Thank you very much. Nice introduction, but I didn't know you were a liar. You said I was smart and that you enjoyed the Bering Sea, and I know the truth is that you got miserably seasick, and if it weren't for the wonderful students you treated well earlier, you would have been in deep trouble. So that's my rejoinder. It's really fun to come back here. I've had a good visit here in years past, and I'm looking forward to this one very much. You can see I have a cast of characters helping me on this. Martin Renner is the genius on a computer for data analysis and figure making. Lisa Eisner has been running the what's called the BASIS program. I don't know what it stands for now, but it's something about Bering Sea and Arctic surveys, and she's provided some of the zooplankton work. Kathy Kulitz was one of my former students and was helping getting a lot of the bird data in the recent years. Carol Ladd, a really wonderful person from the Pacific Marine Environmental Lab of NOAA and physical oceanographer, and Sigrid Sallow, also from that institution, and a genius at downloading and pulling ice data together and a bunch of other things, and one of those rare people who enjoys the idea of going up and camping on the North Pole in early spring for a bit. So that's sort of the cast of characters. They've all helped on this and others as well. What I'm going to do first of all is introduce you to walleye pollock. Some of you probably know it from eating it, but you weren't told you were eating it. You were eating whitefish or some such thing as that. But it's a fish of major importance. Then I want to. That sort of sets why we care about the southeastern Bering Sea. We might all care about it for other good reasons, but it's the commercial stuff that drives the research up there and the resources. Look at the timing of sea ice retreat, something I think is probably quite important. Look at the prey that the pollock eat, and that will tie into the availability of sea ice algae. And I won't talk about it, but there's a really recent paper by Ken Coyle that says that the most important thing from the ice is the cold water that allows the zooplankton have enough energy to get through the winter. And then I'll switch to seabirds and try and tie seabirds into this system, both in terms of where they are and when they're there, but also what they're eating and how that might affect things. And with luck, I will get to some implications at the end. Walleye pollock fisheries are really it's the biggest food fish fishery in the United States, maybe in the world, in terms of food fish as opposed to getting fish for reduction. Those numbers are a couple of years out of date. Then those values are ex-vessel prices values rather than long-term values, but when you get through the wholesale and get to retail, so forth, it's a multi-billion-dollar industry in terms of what it supports. Most of it is landed in Dutch Harbor, Alaska. It turns out to be the #1 port for weight, and it's the #2 port for the value of fish landed. There's also red king crab and tana crab and snow crab coming in there. But the big kahunga is this walleye pollock. Do you know what for those of you who are students and learning about the ocean, what's the #1 port for value in the States? Any guess? New Bedford, because of the scallops. They get a lot of them, and they're very, very valuable on a per pound basis. So this is the eastern Bering Sea, where we've had some adventures in the past. All those little dots are the places where the NOAA Fisheries Bottom Trawl Survey is done every year. So they're about 20 nautical miles apart. And that's a fabulous data set to have. It goes back into the 70s, but they changed gear, so they're really comfortable with dealing with things back to the early 80s. The little light lines are these little lines here, these little light lines are where there's acoustic surveys done, and those acoustic surveys are primarily for euphausids, but they also look at the small pollock that are up in the water column and are not caught by the other bottom trawl survey. And most of the part I'm going to be talking about is this area here. It's most of the research that we put together for this presentation comes from this part here, where the highest density of bird data over the longest period of time. So fishermen and fisheries like to have things predictable and even, so that you can develop your various markets, and you can tell your buyers that you're going to deliver so much fish each year. But as you can see, there's a lot of interannual variability here. Each one of these dots is a year. Now, why do we have many lines? It's because every year there's an assessment model created, and then to see how good that model is, it's fitted to all the past data, and it may even go and be bold nowadays and predict a couple of years out. There you are. Those are years that they say, well, this is where we think it's going. So the important point for the moment is that the biomass out there can vary from 12 million metric tons down to less than 5 million metric tons, which is a big swing. And that's primarily driven by differences in the strength of year classes. So here's the estimated year class strength, number of one-year-olds that must have been there. These are not real data. They're the output of a model that tell you if you're going to have as many fish as we caught later on, that's how many age ones must have been there. And the 95% confidence intervals around these typically are very broad early on because they're not confident they've got the numbers exactly right, and then they get tighter as they realize exactly how many fish must have been there. These data are very telling about how much or how many age 1 pollock are there. But they don't really tell you what the year class strength is entirely, because there are two issues for year class strength or survival. One is the number of spawners, so the more fish that are spawning, the more young you should have. And then what happens to those? Do they survive or not? And where I'm interested in as an ecologist is what affects their survival? What affects the probability that one of these little characters is going to make it to be a 3-year-old or a 4-year-old and then get caught? So the emphasis that for a lot of the things that I have done and have started doing, I'm now going back this way and looking at number of young surviving to age 1. Again, this is an estimate coming out of the model. We do not know, and it's probably true about everywhere, we don't know in hard numbers what's anywhere, because you can't sample all of the Bering Sea and know that you've counted every fish. And if you have, you've killed every fish, especially if you used a troll. Okay, the climate up there, the weather, and this is really an emphasis on climate variability. This is the depth average temperature at a mooring, in the southeastern Bering Sea, in that area that I pointed out where we care about. Every year it gets cold in the winter and it gets warm in the summer. It gets cold in the winter. But when you look at the anomalies, you see we've, in recent years, and His Honor here was out with me in 97, 98, and 99, and 99 was a very cold year. We were out there in mid-May or early June, and there was still ice in the water, not much. But cold periods, warm periods, cold periods, and if this thing was extended, we've come back into another warm period. This is very nice because we can look at the impacts of variability in which the warm periods are probably pretty close to what we'll get over the next 20 or 30 years. And the cold periods are sort of what it was like back in the 60s or 70s. So we've got a really nice range of environmental conditions. And it turns out when you look at these basic environmental conditions down at temperature index, doesn't matter a whole lot what. In the warm years, 2000, 2005, these are the warm ones. Pollock didn't do very well. Cod didn't do it very well. But arrowtooth flounder did. Well, why would you care? Arrowtooth flounder is a nasty predator. It lives off the shelf, and for a long time we didn't know what to do with it until our friends in Asia figured out that the fins were really tasty on sushi. And so they've also figured out a chemical means of stopping their flesh from falling apart. Otherwise, in 20 minutes, they're bags of jelly. So although almost all of what I'll be saying is about pollock until I get to seabirds, think also that this is important. The variability driving pollock is probably also similar to the variability driving Pacific cod, which is the second most valuable whitefish up there. Other than halibut, groundfish. Okay. A while back, I've given you this idea that there's variability up there, and pollock varies a lot. These are two graphs put together by Franz Mutter. He was part of the et al., which is always sad when good people get hidden as et als, or even worse, and others. And what you see here, whether you're looking at age 1 or age 0, it looks like very warm temperatures, surface temperatures, are not good for them, and very, very cold temperatures aren't good. The very cold very likely is that it is too cold for the eggs to hatch or the larvae to grow well. The very warm, well, that's the story here that I would like to tell you. My version is not that it's too warm for the critters to survive the winter, but my story is that it's got something to do with ice and ice algae. Okay, so let's look at variability in ice. And there's two ways to do it. One can look at sort of the shadow of ice of the summer before. This is what's called the cold pool. The darkest temperatures here are -1, and the warmest that they count as part of the cold pool is 2 degrees, and this is taken in June and July. So this water is formed, this cold water is formed when ice melts, sinks to the bottom, or gets mixed to the bottom. Actually, it's fairly fresh, but it gets well mixed at the end of the winter when the ice melts out. Then, as the summer comes and the winds die down, you get a cap of warm water, a very strong picnic line, driven by temperature, not salinity, because the salinity has been mixed all the way through. And then you have that as insulation that allows this cold pool to persist actually from one year to the next. So that tells you something about where the ice has been and maybe how long it was there, maybe. I like this, which is a graph that Sigrid put together for me. And this one looks at the darker the colors, the blue and black is lots of ice. Then you go to the warmer colors, and white is no ice. And what you see here is you get some periods of time, like the early 2000s, when not only did the ice melt back very early, these 2 years, but there wasn't much of it. And then in the more recent years, you have a huge amount of ice, and it stays around quite late. And that's very similar to what we had in the early 70s and is this thing working? Yeah, it is. Early 70s and early to mid 70s. Okay, so what do we know about pollock prey? This is very quick. The important thing for you to take away here: this is what an adult would eat. This is what a juvenile, whatever that probably means, 1 year old and maybe some zeros. Their diets are very, very similar. So the first thing to think about here is that the adults are potentially in competition with the youngsters. For, in this case, copepods and euphausids. And both of them do a little bit of cannibalism. This black here is eating. I believe that's the right. No, this green is cannibalism. So here you've got the adults being cannibalistic. It suggests the young are not, but if we look at diets from warm and cold periods, or late ice retreat, early ice retreat, what you notice here is that in the warm periods, even the age 0 pollock, that black is other pollock that are being eaten. So they're eating their smaller brothers and sisters. And they're, in the warm years, the amount of euphausids, which are, in the greens, is small, but in the cold years, there's tons of euphausids being used. And what I don't quite understand, here's the copepods that should be important, Colonus marshalli in particular. It's important in the warm period here, and I don't see it being used in the cold period by these youngsters. But I know from other people and other stuff that it is, in fact, very important. That's just because those particular surveys didn't catch that. One of the things that's very interesting is that in the warm periods, Ron Hines and others looked at the energy content of the age 0 pollock going into winter. And the red dots are energy content per fish. And you can see with when it's red, it's relatively low. And it turns out that the energy content of these fish going into winter back in this early part here were about the same as the energy content of young pollock in southeast Alaska coming out of winter. So these guys were going in with a really bad deficit in terms of food. So they then have looked at the survival of these young fish to age 3. So this is sort of the size of the age 3 cohort and the energy content of those fish when they were age 0 in late summer. And you can see that the R-square is 0.68. And that's a pretty neat thing to be able to say, that the survival to enter the fishery, you can get almost 70% prediction by looking at the fat content. So people then pushed it back a bit and asked questions about what happens with the mean number of large zooplankton and age 3 pollock abundance. And here, and I don't quite understand, maybe it's because another year came in or whatever, but the R-squared is 0.77. That means that in the fall or the late summer of the 0 age year, if you know how many large zooplankton, the lipid-rich zooplankton are around, you can predict pretty well how many fish of that cohort are going to make it to age 3. And I think most of us find that for most fish species, what drives year class strength is a total mystery. And I think this is getting darn close to figuring out why it is. Okay, so where does ice come into this? I guess I have to hang on to this, don't I? I have to stay with it. I know I'm not going to do that. In the spring, you get a spring bloom once the water has stratified. You also get an ice edge bloom as the ice is melting and it's beginning to release fresh water, and that stabilizes the water column. Maybe only a meter thick, but it stabilizes it a bit. It turns out that the C1s, that's the copepodite 1 stage, so it's the first copepodite stage after the nauplius stage. And what's interesting here is that if it's a late winter, there's no gap between the ice algae under here, the ice edge bloom, and the open water bloom, all coming, and they all come they're all available right here. But if the ice melts back early, a warm year, then there's a gap of maybe a couple of weeks between when the ice disappears and the ice algae disappears with it, and there's enough heat in the water to start allowing stratification. Now, this is still hypothesis. It's the best guess we've got. But we do know that a lot of these these Thysana esaraceae is a euphausid, Marshallii is and glacialis, it's not quite clear what species it is these days, is a very large lipid-rich copepod. This is a large predatory amphipod. The important thing here is that when you look at the fatty acid, the compound-specific fatty acid, so you're now looking at the carbon in those items that aren't being turned over once they're incorporated into an organism's body. But they then tell you where that carbon came from, because the carbon isotope ratios are different in sea ice than they are in open water algae. And so bingo, somewhere between 30 and 70% of the carbon in these large critters is coming from ice algae. And that to me is a pretty good way of linking the importance of ice algae and the importance of having it around at the time that these critters are growing and need to take on a lot of energy, and their availability to the fish. And so one comes up with I love cartoons and bits of silliness. So here's a quick cartoon. Not too many zooplanktons and mostly small. Some of that goes to the big fish, but in fact, the big fish don't get enough, so they then are more cannibalistic. And of these little ones that are around, they're thin, they're small, and they have a low survival rate getting to their second and third year. In contrast, if you make an argument for a cold year or with late ice hanging around and the blooms hanging around with it, then there's lots of zooplankton for the big fish to eat. They still eat some little ones, but not as many. And the little ones have a much better survival through. So that's my story. Ken Coyle, and I think it's important to know that there are alternate ideas, would say the biggest thing is this is all very well and good, but if these guys don't survive the winter to then lay eggs and grow new youngsters, there won't be much zooplankton around. So there are two things that we need to sort out: the relative importance of cold water and conserving energy because the metabolic rates are lower, and ice algae and production of eggs and production of growth of young. So that's the summary there. The euphausids, these things all have lots of lipid in them. That's when you look at a vial of these things that it's an alcohol. The alcohol is pink and often has a little sheen of oil on top. That's coming from inside. I think the variation in timing affects the abundance of euphausids, and those in turn affect what's going to go to pollock, how well pollock will do. So let's now look at some seabird stuff. This would be even more dramatic if we had the last 2 years of data in here up to 2014. But basically, every one of these little dots is a 1 kilometer long bird survey effort, or actually 3 kilometer long bird survey effort. So we have a pretty good density, and we started in 75, and that pile of good stuff goes through 2014. We started off by looking at what's happening with those birds out there. And so we just ran it by year. For each species, a separate line, separate color. I call this my spaghetti diagram. Very discouraging. But if you pull them all together, you see that there were quite a lot of birds around, and they went down, and they went up, and they went down, and they're actually coming up again. So there's a little bit of underlying pattern, and the colors up here represent warm and cold and normal sorts of ways. And it turns out that a lot of these high numbers are when it was cold. So we pursued this a little bit further. First of all, I'll talk about annual rate of change. Some species of birds appear to increase. These are 95% confidence intervals, which means you feel rather weak in terms of confidence in any one, but there's clear that there's probably more species that are actually showing some decline than those that are increasing. And then we wanted to say, okay, how does that relate back to that spaghetti diagram and warm and cold years? So we classified 40% of the years as cold, the coldest or the latest ice retreat, and the 40% with the earliest ice retreat as warm or early years. And when we look at that, we see that this is essentially densities in early years versus late years, and Densities in early years were greater when it's up here, and densities were less down here. And these are on a log scale. So there are big changes. Because of the sampling, you can't have tremendously great confidence in them. But when you look at these as a whole, you say, early, those years with early ice retreat, you lose a lot of species. But you actually end up with more individuals around, because this little bar here represents shearwaters, and they're by far the most numerous species there. The shearwaters we have are almost exclusively short-tailed shearwaters. They come from Australia. They breed in Australia. They come up to the Bering. They gobble euphausids and some baby pollock, and then they head back. So they seem to be perhaps more numerous there, but overall they have declined. I also then wanted to look at the distribution of the birds on the shelf. And we started out with I guess I need to go back here, a hypothesis. It's always dangerous because almost every time I come up with one, I'm wrong, which is satisfying in a way because it says I'm being honest about my science. Frontal areas are places where prey tend to aggregate. And the stronger the front, especially convergence fronts, the more likely you are to get stuff aggregating near the surface and good opportunities for foraging. So our hypothesis was, we were thinking of the warm years, and I was focused on the zooplankton. There would be less zooplankton. And so with the lower zooplankton amount, we would see birds going to the frontal areas. So we looked at that, and lo and behold, there's absolutely no difference. If anything, there are more birds going to the non-frontal areas in the warm years. So we're left with, okay, that hypothesis didn't work. So what else can we do? Well, we looked at cumulative frequency distributions. My statistical friend, Martin Renner, really, he fought me tooth and nail over it. This is just too simplistic. But my goodness, it's easy to see for some species, the red and the blue lines coincide almost perfectly. Very little change from warm to cold or early to late years. And other species shifted quite a bit. And so then I let him start playing with fancier graphs and asking what was happening. And what essentially this says is that if it's below the line, then it's a decrease in early years or warm years. It's above the line, there's an increase. So shearwaters increased in the middle and central part of the shelf, an inner shelf, but they decreased in the outer shelf. And similarly, you can look at diving species of birds. They sort of came in a bit and they dropped off in shallow, and they might have actually gone to frontal areas in this area. And then the surface feeders increased in the middle shelf. And that was a surprise. It shouldn't have been, but again, it's one of these problems that you get your mindset on, say, the zooplankton, and you forget about the other things. So here's another way of looking at this. The offshore, this depth down here is the mean depth at which a particular species is seen in all years. And you then ask, do they move, when it's a early year minus a late year, so are they moving inshore or offshore? And if they're down below this line, they're moving inshore, above this line, they're moving offshore. And what it looks like to me, and it's probably even statistically significant, this line is statistically significant. Those are the 95% confidence interval. These characters that live in really deep water off the edge of the shelf are moving onto the shelf, and others that are in really shallow water are moving out into deeper water. That was all of that together was a bit of a surprise. And what I think is interesting here is that when you look at this graph a little more carefully, you realize that the story for the pollock, the age 0 pollock, is really different than the story for the zooplankton. So in the early years or warm years, no argument. The zooplankton, the euphausids, the Calanus marshalli, even another species of copepod that's along the shelf, the indications are that they're not doing as well in the early years or the warm years. But age 0 pollock are much, much more abundant in those warm years. And these are the ones that are skinny. And I haven't been able to get the pollock people to give me a straight answer on this yet. But my sense is that maybe these age 0s are hanging around up in the upper water column, hoping to find some more food so they can fatten up and get to some minimum amount of fat before they go deep in the water column. And so when you look at the distribution in, this would be a warm period and a cold period here of age 0 walleye pollock in the top 20 meters. So this is a surface troll. See, these little age 0s are everywhere and in high densities, whereas in the colder years, they're here. But those that are here are probably fatter and happier and are going to survive. So again, you have to look beyond just the numbers and look into things like the quality. So for seabirds, there's a big change in distribution. With years with early sea ice retreat, there's less zooplankton, more age 0 pollock, and these guys they don't go to the frontal areas, but they do go into the middle domain. The changes in overall abundance is work that Martin Renner is still working away at. Overall, more species declined than increased, and the patterns of decline and increase were very particular to individual species. My argument, and that of a few others, is that the algae that grows on the bottom of the ice is really critical for the large copepods and euphausids to develop, to grow fast, and to put down a lot of fat or lipid. And these zooplankton then are important for the age 0 pollock and help them survive. I think the seabird story is a little murkier. As you could see, those graphs are not as clear cut, but my sense is that we've had a decrease in numbers overall, and that these things are shifting back and forth across the shelf and telling us something about where food is available, and in particular age 0 pollock. So what are the implications of this? If the Bering Sea ceased to have seasonal sea ice cover, which you could see we've already had some winters when there was virtually none. But if that becomes the norm, we're going to see smaller zooplankton species. We're not going to see these big lipid-rich jobs, and we're going to have a less efficient food web. So it'll take another step or two to get up to the larger things that the fish and the birds will use. I'm willing to predict there'll be low recruitment of both pollock and cod, probably fewer seabirds, and added to this mix is that the large whales are increasing up there. Whether they continue to do so if the zooplankton isn't there, I don't know, but they eat small fish as well and herring. And so if you were a pollock fisherman, I would not be advising you to go and buy a new vessel right now, or a cod fisherman to go and buy a new vessel, because if this scenario is right, then those fish are going, both cod and pollock, are going to have a hard time. Thank you very much. I'm open for questions if anybody would like them. Yes.
Naive question. I'm from Michigan. We had walleye there. I thought they were a lake fish. I didn't realize.
The question was about walleye in Lake Michigan. And yes, that's a walleye perch or a walleye pike. It's a totally different fish and a different family of fish. This is a pollock. It's a cod relative. In fact, it used to have a tongue twister Thoragora as its generic name, and it's now gone to Gaddis, which is the genus for cods, and very close to the Atlantic pollock. But a different fish, and nowhere near as bony as a walleye, if I remember rightly. Other questions? Yes.
You're a guy who goes out, samples, a scientist who goes out on, say, a NOAA ship and samples, and gets samples.
Right.
What I really noticed about the Bering sampling pattern is that's a grid pattern.
Yes.
Whereas here in the Northeast, in the Northeast survey, it's random. And when you go out, you never know where the ship is going to go because they've got a random pattern in mind. Do you see an advantage in the grid pattern of sampling that advantages research?
Okay, the question was that in New England waters, the sampling by NOAA for groundfish is done on a random pattern basis, whereas in the Bering Sea and in the Gulf of Alaska, it is a grid. I'm not enough of a statistician to know, but at least if you are sampling the same place over and over again, you know that place is not going to be a variable that you have to try and account for. Whereas if you move around, in theory, if you've covered all different kinds of habitats, in the end you should have a good sample of what was there. And so statisticians probably prefer the randomization pattern, and maybe natural historians like me prefer the other because I can then look at a particular area and know that it's been sampled the same way from one year to the next and ask, have the birds in that area changed or have the zooplankton changed, and not have to expand my area to get enough samples so that within the random sampling I can compare years. But I suspect that you get just about as good or maybe even better with the random if you're looking at the area as a whole. But if you're, let's say, a bird watcher riding along the vessel, I would at least prefer to be on a grid pattern and know where I was relative and where I was going to be. But it's a pretty fantastic survey effort they put in up there. The eastern Bering Sea, that grid from the that shelf is about the same size in area as the states of Oregon, Washington, and California combined. So you see these little maps, and the Alaska is a little tiny place. You can put 5 Texases in it or something, and then you look at the Bering Sea shelf and you say, oh, one vessel's plenty, that's a tiny little place. But it is bigger than those 3 states combined. And for a long time, the only vessel up there was something called the Alpha Helix, in which we have worked. And it could go 10.5 knots. So that was about the same as trying to survey those 3 states and all their habitats with a 10-speed bike. I mean, that's the perspective that we lose when we have these nice maps and they're all squished down.
So I can imagine that they don't get to do the entire grid every year, depending upon ice or what.
They do it in the summer. They do the entire grid. They try to start on the exact same date. They go in the same order so that if there's any temporal shift in where the fish are, they will pick that up. They're not going to be aliased by that. And there are a few years where they go all the way up essentially to Bering Strait. But that's now starting probably on a once every 3 or 4 year basis. It's expensive. But on the other hand, we have done very, very well with most of our fish stocks. I mean, we don't, over the last few years, our present red face is a very major decline in Pacific cod that has occurred in the Gulf. There was a warm blob of water that came in, lasted 3 or 4 years, and a very strong year class from 2012 seems to have disappeared, and everybody was counting that as the year class that was going to sustain the fishery until the next strong year class. Other questions? Yes.
It sounds like you have a lot of acoustic data on the distribution of the stations in the Pollock.
Mm-hmm.
Has there been any efforts on trying to correlate that data on the distribution of feeding flocks or the distribution of bird species over Bering Sea?
The question was whether or not there's been an effort to use the acoustic data for euphausids and small pollock to sort out where birds might forage. The answer is not yet. There has been some effort to say that when net sampling or acoustic sampling shows very few euphausids around, shearwaters tend to move up into the Chukchi Sea or the Beaufort Sea earlier and in larger numbers to forage up there on euphausids that are being blown up in the Anadyr water from the shelf edge and from the Gulf of Anadyr over the Russian side. But most of the area there, the euphausids are too deep. There's nothing that's going to concentrate them. I have worked on euphausid for birds foraging on euphausids where the euphausids are being pushed up against a ledge or a shallow sill, and there's some point at which the tide going across that sill just matches the ability of the euphausids to swim down, and so they get aggregated, but they're also aggregated more shallowly, and then the birds just come in and hammer them. But the second the tide turns, they're gone. The birds are gone and the euphausids are gone. They just back down to depth. Any other questions? Yes.
So I'm curious about your just amazing bird sampling method. It seemed like from that figure you have hundreds of points. I think you said 3 kilometer transects.
Yeah, I think.
You sail.
Yeah.
And I guess I'm curious 2 things. One, is it a single observer transect on the boat? And then 2, what's the length of time that it takes to complete the whole transect sample? Not each sample, but the entire sample.
The entire survey that when they're on the fisheries vessel, I think is on the order of maybe 5 weeks, but I'm not sure. It's a long time. The bird samples are each one of those little things. Since we count out to 300 meters, each one of them is about 1 kilometer square, and there was a change in methodology due to my screwing up way back when. I had been working up there for maybe 10 years, and we came up with this idea that you should do snapshots. You should count the flying birds and then stop, wait 20 seconds or 30 seconds and count them again, because otherwise you're getting a much higher count than you would if you just flew over in a satellite or a drone or something. And more recently, people have chosen to switch to the actually better method, and we then had to figure out how to combine these 2 data sets. And what we did is we went back to the literature and people who had wrestled with this problem in the Antarctic and other places and figured out bird speeds and what each bird species would be likely to do if flying at random across the transect, because eventually it would be at random. And then we published those as correction factors. So it's not perfect. Usually, you have an observer and and somebody who's entering data. Particularly if you're close to the islands. If you're out in the middle of where it's slow, you just have an observer. But not everybody can afford 2 or 4 people on the ship at a time, and not every ship will take that, say, 4 bird observers, so that you have 2 teams of 2. So you do what you can. The basic techniques are similar. 300 meters, so you're not bedeviled by weather and who has the better binoculars, things of that sort. There is the problem of changing a method, but we have now published several papers on this. We've been straight up about that needing to be changed. We've tried to get, and we get patterns, but as far as I know, we don't have anything that says, oh, the day that changed, or in that period suddenly everything went down or everything went up. Any other questions? Yeah.
George, do you see any different species coming into the area? You mentioned the whales were increasing with different species.
Well, my sense is the whales are increasing because we've stopped killing them. So this is not some whales that have never been there before. They're reclaiming as their populations grow. Because we've got better coverage, we're seeing more of these weird birds that come from the southern hemisphere or whatever and wander all over the northern hemisphere during their winter. And so we're getting more counts of things like mottled petrels. It's quite clear that there's been increases in albatrosses, but for Laysan and certainly for short-tailed albatross, that's still on the endangered species list, they're increasing. Blackfoot might be a shift in black-footed albatross. It's one that's normally more down Gulf and down into California even. So I don't know if the increased numbers there are due to what they're due to. But they might be one where there's an increase. But they were there before. They were just very scarce. So I don't see, the cardinal that when I was a kid here in Maine, the nearest cardinal was somewhere in southern Jersey. And it was a really big deal when I was about 16 or so that the first cardinal was seen in Massachusetts and down on Cape Ann, and everybody went to the feeder from all over the state to see this. So, and now, Steve tells me he gets cardinals in the backyard. So there are a lot of changes in the land bird fauna, but I don't think so far in the Bering in terms of species composition. Anything else? Well, thank you very much. It was good fun being here.